Start recording now. So this is lecture number 8, I believe. And we are on slide number 32. So everyone, please turn to slide number 32.
Professor, I had a quick question.
Yes, go ahead.
So I know you wanted us to use Crunch It for the lines to find R, but was that the only way to find R?
Well, Crunch It is a program that
Well, I know they had that really long equation where they had that typo in it to find R, but
yeah.
like you said it was too complicated. So do you think it would just be more practical for us to use Crunch It in general?
Well, do you have access to Crunch It?
Oh, I thought it was just something you could look up on Google. I didn't know. Is it something you have to pay for?
I believe it is.
Oh, okay.
However, there are, I mean, if you have a calculator like this, you can certainly use that.
Yeah, I have the TI-84.
Yeah, so TI-84 will do everything in that regard that Crunch It can do.
Okay, cool. Thank you.
It's just you have to know how to plug it in. I think we covered that last time, right? I showed you how? I don't remember. Did I show you guys how to use the TI-84 to calculate it?
I don't
think you did, but can you go over it again?
Yeah, I don't think so. You did.
Yeah, I don't mind. So let's find data. Let's use the one on slide 31. Okay, so I'm going to walk through how to plug this into a TI-84 from the example on slide 31. So what we have here is we have 5 data points connecting children to cars. And as I mentioned last time, the numbers are staggered. So the 4 goes with the 3, the 1 with the 1, the 5, 3, 2, 2, 3, 2. So the first thing you do is you hit the stat button right here, stat. And what pops up is edit, calc, and tests. We're not ready to do any calculations and we're not ready to do any tests because we don't have any data yet. So we're gonna edit. We're gonna hit enter. And what you get is you get 2 screens or 2 lines, L1 and L2. And you're gonna put your data in L1 and L2. The X values in L1 and the Y values in L2. Okay, so if you have data in them already, you have to clear them. And the way you do that is you go up to the top so that you highlight L1 or L2 and you hit clear. And then you go back down, you'll see that it's now empty. And if I go over to L1 and again, I scroll up to the top and I hit clear and go down, again, now L1 is empty. Okay.
Wait, Professor, how do you get to the graph? Sorry, you cut off when you were explaining. How do you get to that?
Oh, you hit stats
point.
You hit stat first, and then you just hit enter after you hit stat. You see the stat button right here in the middle?
Thank you.
Okay.
Mm-hmm.
Okay. So let's put the data in. In the first column, we're gonna put in 4, enter, 1, and 4, enter, 1, enter, 5, enter, 2, enter, 3, enter. So when I do that, the first column now has all the X values, 4, 1, whatever they are. I can't read them backwards, but 4, 1, 5, 2, 3. And then we scroll over to the next column and we do 3, 1, 3, 2, 2. So now we have 2 columns. Okay? You with me so far? I need to say I haven't. Oh, most of the grades are up, not all of them. I'm still going through all the emails. If you're not up, it doesn't mean anything bad or good. I just haven't finished all of them yet. Okay? But a lot of the grades are up already, just not all of them. Okay, so still working on it. I readily admit that I took too much upon myself this semester, teaching 8 classes and taking 1. And It's more than it's more than I should have done, and I apologize for the repercussions on you for me being a little late in getting things done. I am sorry, but I made a mistake. That was my bad. I thought I can handle it because I'm a workaholic and I love working. Well, thank you. I appreciate that, but it's just things are taking longer than I would like, and I'm sorry. I guess the good news is I'll probably give you less assessments, only because that way I have to grade less. So I guess on your end, it's not the worst thing in the world, but I do apologize for that. I know you're okay with that, and it's a different semester as well. But anyway, so at this point we have all the data in, correct? So now what you do is you hit stat again, but this time go to the right to test, to calc. Okay, we're gonna do some calculations now. Now that we have the data in, we're gonna go to calc. You see that? Okay, and if you scroll down to linreg ax plus b and you hit enter, it's just gonna ask you to go through some, hit enter a few times to calculate, and then you should have a screen that looks like this. And that screen tells you your a and your b, your slope and your y-intercept, because ax equals b, ax plus b, and it gives you your correlation coefficient r, and it also gives you r squared. Okay, so it gives you all of this information that we need. Okay, so that is your calculator. Now, I'll say something even cooler. What I want you to do, so first, are there any questions on that part?
Excuse me, Professor, I have a question.
Yeah.
On my calculator, I have a TI 83 plus, but it only shows the A and B. It doesn't show the R and the R squared.
Okay, so here's what I want you to do. Hopefully it's the same as mine. Do you see in the bottom the word catalog in blue?
Yes.
Above the 0. So go to second and hit catalog. And then I want you to scroll down, and you're going to go a long way down. And this is for anyone who doesn't have the R's. You're going to go a long way down to diagnostic on. And I want you to hit enter a couple times for diagnostic on until it says done.
Okay. And you said it's all the way at the bottom?
No, not the bottom. I mean, it's D. It goes to A to Z. It's just not, right away.
Okay.
It's alphabetical order. So you go to D, you go to diagnostic on, and then try it again. Hit stat, calc, AX plus B, and this time you should see it all.
Sorry, Professor. For me, it kind of was a little cutting out when you said right before you go to calc and then linreg. Where did you go in the beginning? Did you go to graph?
No, I'm not graphing anything yet.
So what did you press in the beginning again? I'm sorry.
Did you put your data in yet?
No. I have everything after calc linreg, but before that, I couldn't really hear you.
Oh, go to stat.
Stat.
Calc. Linreg.
Oh, okay.
Thank you, Professor. It shows down.
Okay, good.
Professor, when you get time, are you able to help me figure out my settings on my TI-84? So when I use inverse norm or the norm CDF, that I could have the left and right thing?
Oh, that I've never done. But if you want to stay after class for a minute, we can do a Google search and see if anyone's ever asked that question.
Okay, thank you.
And I can help you walk you through it. So now let's do something even cooler. Hit seconds, top left, and above that button, hit the Y equals. You're going to see a stat plot, right? In blue, stat plot. Okay, and the first one that you want to do, you want to hit this on. Right, so the first stat plot, you want to make sure it says on. If it says off, just hit enter. You get to this screen, and then you want to toggle between off and on. You want it to be on. Okay? Does that make sense?
You said second, then what?
Stat plot. Top left button, Y equals. Second takes you to blue mode. So you're going to be looking at all the words on top of the buttons. They're all blue. Stat plot is the top left button, right? It says Y equals, and above it says stat plot. Yes?
Yeah.
Okay, acknowledge. Okay, so hit that, and then make sure the first one is on, not off. Yes?
Got it.
Okay, now, next to the y equals, hit the window button. Hit window. We want to set our window. Now, all of our data, all of our x values and y values are between 0 and 5, right? So set x min and x min to 0, x max to 5, y min to 0, y max to 5. It should look like this. You set all of your x min to 0, x max to 5, y min to 0, y max to 5. And then finally, the top left button here, hit graph. And what you should see is a scatter plot of your data.
Where it says X scale and Y scale, do we leave it at 1?
Yeah, leave it at 1.
And then you just keep pressing enter until it pops up?
No, hit graph.
Oh, graph. Okay, there we go.
Okay, anyways, so that's how you use it at TI-84. Let's get back to our regularly scheduled broadcast, which is slide 32 on regression warnings. Okay, what are the 4 things when it comes to regression that you want to be careful about? Well, one is making sure that you're actually looking at a plot that's linear. Correlation only works for linear relationships. If it's not linear, the correlation is nonsense. Now, has any of you taken a basic course in chemistry or a basic course in physics yet?
Yes.
Have you done labs where there was a nonlinear relationship and you manipulated your data, not in a bad way, but change your variables to create a linear relationship so that you can do a best fit line? Have you ever done that in a lab? Hopefully you have. If you're taking chemistry, it's integrated rate laws, we do that all the time. What if we don't have that calculator and crunch it? Then you go online and you Google a scatter plot regression calculator or something, and I'm sure someone's made an applet, a program to do it for you. But don't do these by hands. You just don't want to do it. They're a pain. Find an online resource. They're out there. Everything's out there. So correlation only holds for linear relationships. If it's not linear, you are going to get nonsense as your answers, and you're going to start interpreting it, and it's not applicable because it wasn't linear. So make sure it's linear. If it's not linear, there are ways to make it linear, but we're not going to worry about them in this class. That is done in a lab, physics or chemistry or something like that. And I'm going to spotlight, so I'm big for people who watch this later. Oh, I already spotlighted. When did that happen? Hold on a second. And then, okay. Excuse me. Okay. So, 2, a regression line is used to predict y values. So if I say, what about this x value? I can say, well, I have my regression line, and therefore for that x value, here's my prediction. And you can predict your y value. It does not go in reverse. You don't get to say, well, for this y value, what x value would have given it? That's going backwards. If you want to do y implies x, or predict x from y, start over from scratch. Switch your data, make a new best fit line, and do it from scratch. Never work backwards, only forwards. That's caution number 2. Caution number 3, extrapolation. Suppose you take a scatter plot of heights of people from born until they're 1.5 years old, 2 years old. What relationship do you expect as children are growing from birth till 2 years old? As they get older, what happens to their height?
It increases.
Big shock there, right? It increases. And let's suppose it does increase linearly. Would I be able to say, okay, I now have my best fit line. How tall will an 80-year-old be? Do I expect my best fit line to continue all the way till they're 80 years old?
No, it would plateau.
It would plateau. That's the way it really is. But my data from 0 to 2 years old shows linearity. So I'm trying to use my data to predict something that occurs way outside the data range. That's called extrapolation. Can't do it. You can only make predictions based upon your data. Okay? I have from 0 to 2. I can predict from 0 to 2 because I have lots of data from 0 to 2. You're 80, can't do anything. It's a whole nother situation. Okay? If I was able to predict an 80-year-old be like 900 feet tall, you know, if you keep going linearly, you just keep growing. That's not the way the world works. But the data is from here to here, looks very linear. I am missing all of that plateauness because I don't have any data to support it. So don't extrapolate. Don't go outside your data range. We love questions like that on tests, right? Here's your data range, predict this value. Answer, you can't, it's outside, extrapolation, bad. Something like that, but full sentences. And then the last one, association does not imply causation. Just because two variables are associated with each other, that there's a connection, does not mean that one implies the other. Here's an example, which I probably used, maybe not, I don't remember. The more cars that a person owns has great predictive power for how long they live. So people who own more cars tend to live longer. Have I used this example for you guys so far? People with more cars tend to live longer? No.
Oh.
Okay. This is true, by the way. The data supports it. People with more cars tend to live longer. So does that mean if I really want to live longer, I should go out and buy more cars? Does one cause the other? Or is one associated with the other? Why do you think people who have more cars tend to live longer?
Is it because they have better access to healthcare and better food supplies, like to eat and stuff like that?
That's exactly it. People with more cars are richer. They have more money. With more money comes better healthcare, better resources, better medicine, all the things that you need to live a longer life. Does having more cars imply or cause the other? No, but they are associated. There's a connection between them. So you have to be very careful because in statistics, we cannot talk about causation. We can only talk about association. We can only say these things are connected, but we can't say that one causes the other. How do you determine whether one thing causes the other? Common sense. That's just use your brain. Now, common sense does not always lead us in the right direction. It's true, but as a general rule, causation versus correlation or causation versus association is not a statistics question. Okay, that's a just think about it question. Does that make sense so far? So if we look on slide 33, a lot of redundancy in the next couple slides, and we're going to skip a few of them. But if you look at slide 33, it says again, R is the measure for linearity only. It requires both of them to be quantitative. We do not do correlation with categorical variables. We only do correlation with quantitative variables. It does not work for curved relationships. It only works for linear relationships. It is not a resistant measure. You make one outlier, as we're going to see in a few slides, can have a drastic effect on the correlation. It's not resistant to outliers. And most importantly, it is not a complete summary of two variable data. There's lots of other information that we need. It just gives us one piece of the puzzle. So if you look at slide 34, I would like you to ignore the line that they drew through the graph for a second. And I want you to tell me whether or not the data points seem linear. And if not linear, what is the pattern that you see? It looks like it curves downwards, right? It looks like it's a exponential decay, maybe. It could be hyperbolic. I mean, it could be many different things. However, whoever took this data went ahead and actually did a scatter plot and calculated the correlation coefficient. And what do they get for the calculation coefficient? As written on the slide. Negative 0.86, which indicates what in terms of the strength of the relationship? Weak, moderate, or strong?
Strong.
It's a strong linear relationship. The math says at least. Even though by looking at the data, it does not look linear at all. Conclusion, math is great, but sometimes you got to just make sure the math is appropriate. In this case, the math gives you a strong relationship. Hey, we got a linear relationship, but the data, when you plot it, it does not look linear. And because it does not look linear, I would not try to use correlation. It just doesn't apply. So the best fit line and the R value, okay, the math might have gave them for you, but you wouldn't use them in this case because you would first say this is not a linear relationship. Does that make sense? Sorry. Does that make sense, everyone? Any questions on that? I hope so. I'm getting utter silence from everyone.
This y hat, that's the regression line. That's the...
Oh, so y hat is the regression line. Okay, so that's the line, the equation of the line that best fits the data. That's y hat. Y equals mx plus b. We use y hat. And the R value gives you the strength of the data in terms of how close to a line it really is. R values that are near 1 or negative 1 are very strongly linear. Negative 0.86 is a strong linear relationship if only it actually was linear. But the data does not look linear. And because it does not look linear, I wouldn't even try to use my correlation because it's just not appropriate for the problem. Does that make sense, Sydney?
Professor, do you think we can just review and like the y hat equation in this example on 34 just to see just to run through how we do it like in class?
Well, the only problem is I don't have these data points. I don't have these actual data points, but you know what? Let's see if I can guesstimate them. So hold on. Let me load up Crunch It because I'd rather do it on Crunch It than on my calculator. Okay, so I'm going to share my screen. And so here's Crunch It. Can you all see that? Although I don't have my data in yet. And here is the picture. So how do I... Okay. So let's take a look. I have 3 zeros for x values. Those are the first 3 points, 1, 2, and 3. These 2 are 1s. These 2 are 3s. That's a 4. That's a 7. And that's a 9. Would you agree with those approximately at least?
Yes.
Okay. This first y value looks like about a 3.25, 3.754. This one is about a 1.75. This one's about a 2.5. This one looks like a 1 and a 1.5. That's about a, let's say 0.75. And then we got 2.5s. approximately. It's not going to be exactly the same as theirs, but it's in the ballpark. Would you agree? Yes? Hello?
Yes.
Okay. So we're going to go to graphics. We're going to make a scatter plot. Our x values are variable 1. Our y values are variable 2. And we calculate. Okay, so we get that scatter
So on a
plot.
calculator, our L1 would be the x's and L2 would be the y's.
Yes.
Okay, perfect.
Okay. So my graph isn't perfect, but it's not bad, right? It's in the ballpark. So let's go ahead and now do the regression. Simple linear. Variable 2 is dependent. Variable 1 is independent. Numerical results. So I got 2.97 minus 0.37x. That's pretty close. Right? That's pretty close. And if I do the best fit line, I get that. So I can remove this one. And what is my R value? What is my correlation for variable 1 and variable 2? Negative 0.84. So this wasn't bad, right? I wasn't perfect, but I was fairly close. You see how I did that? Anyone? I hope so. You guys are not the most vocal bunch, but I like you anyways. All right.
So Professor, I tried to do this on my calculator while you were doing it. I input all the L1s and L2s, but after you input them, I know you're supposed to go to calc, right?
Yeah.
Do you know how to go back from inputting the L1s and L2s in to go to calc without erasing all the information?
Yeah, just hit stat again. Doesn't go away just because you leave the screen?
I'm just on the screen right now with the L1s and L2s, but I'm trying to go back to it real quick.
Yeah, hit stat again.
Stat and then calc, and then it was the
linreg.
linreg. And then it just shows X list, Y list, frequency list.
Yeah, go enter through all those, go through them.
And then calculate.
And calculate.
Okay, I got Y equals X plus B, A equals negative 0.36,
Yeah.
B equals 2.96.
That's what I got.
Perfect. Okay, cool. Thank you.
All right. Does your R value shown there too?
No, it doesn't.
Okay, so you got to do the following again. Hit second. And then hit the 0 button at the bottom.
Okay.
Okay, and I want you to scroll down to diagnostic on. So scroll all the way down to diagnostic on.
Okay, diagnostic on.
And hit enter twice. Make sure it says done.
Uh-huh.
Now it'll show it.
It says done, and then you have to go back to where you were?
Well, you got to do it again. Stat, calc, linreg, the whole thing.
Oh, okay. Do I have to keep pressing diagnostic on every time? Or
No. You do it once and it's set.
Oh, cool. Okay, perfect.
Once and it's set. So, I had dinner, and now I have dinner. All right. So, I don't know what you're saying right now, but this is good stuff. All right. That's right. That's right. Okay. So, let's go now to scatter plot. Sorry, to slide number 35. Stephen, it's easy. You go to the website www.makenomonytheirwholelife.com and the sign up is right there. So that's that's the best place to do it. So slide number 35, we have an example. I think we already says makenomoney.com. It said he was rich a few seconds. Well, I'll tell you this. I work probably about 80 hours a week to make a solid living. However, if I only had one job, as opposed to the 4 that I have, if I only had one job, then I would not make a lot of money. But you multiply that by 4, and yeah, it's tough life. You see that TV in the background? I never even watch it. Do we have to look up scatter plot maker or something like that on Google if you don't have Crunch It or the calculator? Yes. If you have a problem that requires it. I don't think we would ever ask you to make a scatter plot of your own. Maybe on homework, but I don't think on a test we would ever ask something like that. Please don't. Well, the tutoring pays good too. Well, one of my jobs is tutoring, so she begs. Well, in that case, but you should certainly. Excuse me. I'm sorry. You should certainly check it out, Sydney. Just go online and see if you can find one, just so that if the situation arises where you would have to, it wouldn't be the first time. That's all I ask. But anyways, slide number 35, example of extrapolation. So what we have here, sorry. Well, that's the thing. Well, let's take a minute. Let's see if we can find one. All right, let's see if we can find one. So I'll do a Google search, Google. So scatter plot, calculator line of best fits. Let's try that one. Okay, so the very first link, you put, it's not letting me put in my data. Oh, here, add points. Like 1, 3, add points. 2, 5, 2, 4, add points. 2, 5, add points. I don't know, 1, add points. Let's just make sure that you can go more than 5 points. Okay, so you got these points, right? You can keep adding points. Show line of best fit. I don't know what the guess is, but so they're giving me the line of best fit, but are they giving me the equation of best fit? Oh yeah, right here. X plus 2, R equals 0.36. So that was the very first link that I found, and it gives me a perfectly valid scatter plot calculator. Right? So, right, Google is a reason why they're pretty good at stuff.
So when you get that equation where it's y hat equals 10.82 minus 0.113x on slide 5, when you get that kind of equation, because I know it's y equals ax plus b, and I just did all that work on the calculator, you're basically just inputting it into that equation.
Yeah.
So why is in this case y hat equals b minus ax?
Well, b plus ax where a is negative, but yeah, basically. Right?
Oh, okay.
Okay, so we get y hat equals 10.82 minus 0.113x. It says interpret the slope. The slope says, the slope is negative 0.113. What does that mean? That means we drop 0.113 for every 1 unit to the right. What does 1 unit to the right mean? We increase our mileage by 1 unit. What are the units? 1,000 miles. So if I have 1,000 more miles on my car, the Y value, which is the selling price, should drop by 0.113 units. The units here are thousands of dollars. So for every 1,000-mile increase, the selling price drops by $113. That is what the slope represents. Now the y-intercept is 10.82. When x is 0, you get a y value of 10.82, which says that if there's no mileage in the car, if it's new, that the selling price should be $10,820. Does that seem reasonable? Does that seem reasonable? Well, it does seem reasonable because car prices can be around that point. But remember, our data goes from what X value to what X value. What is the range of our data? From what to what? Look at the smallest X value and the largest X value.
18 to 35.
18 to 35. So to take that data and to say that it applies to X equals 0 would be called extrapolation. Would be going outside of my data range. And I can't say with certainty that the pattern continues that far. And therefore, I would not be able to predict the selling price of the car. Does that make sense? Yeah, okay. However, what does 10.82 mean physically? It means times 0. That should be the selling price. It's just I can't reliably say that because of extrapolation. Okay? And the same thing goes on the other side. Once the car passes 35,000 miles, now my selling price is negative. Does that really mean to say that, okay, once it's past 35,000, I'll pay you to take it? That doesn't make any sense. So you don't want it anymore, just drop it off at the junkyard or something. You don't pay someone to take it. So the equation is only valid for a given range and don't go beyond it. So now I'll delve a little more deeply into association versus causation, okay? The lower left picture here talks about X being the cause of Y. And the reason Y occurs is because X occurred. X causes Y, straight up. There's no other reason why Y should occur other than X. In that case, would I say that X and Y are connected, that they're associated if X causes Y? Is there a connection between them if X causes Y? Sure, 100%. There's an association, but there's also a causation. In the second slide, or the second picture, no, we don't do causation. I'm not saying that we can conclude causation. I'm just saying, can there be causation? Right? You can have a situation where X causes Y. You might not be able to conclude that statistically, but in practice it can exist, right? I mean, it's theoretically possible, right? Waiting for you to respond because this is like the kind of like the head nod if I was actually in a class. Okay. Specifically, if somebody asks something in the chat and I answer it, I just acknowledge that you still understand or that you don't or something, so I can move on. People don't say anything, I don't know what's going on. Now the second picture is different. The second picture is a situation where Z causes both X and Y. Whatever Z is, I don't know. You know what it is? I'll give you an example because there's a great one on the next page. People, or if you look at children between being born and let's say 18 years old, the bigger the shoe size, the better the reading ability. This is fact. If you look at children from the age that they're born until they're 18, the larger their shoe size, the better overall their reading ability. Does that mean that shoe size causes, or a higher shoe size causes better reading ability? Does that seem reasonable? No. Is there something else that causes both of those to explain the connection between them? What is it? Yeah, exactly. Okay. The older they are, the bigger their shoes. The older they are, the more they've been in school. It makes sense, right? So you have one thing cause two different things, which themselves have an association. So statistically, you wouldn't be able to tell that unless you saw the common cause. Okay, so the first case, one thing applies the other straight up. We're done, easy. But sometimes two things are connected, but there's a cause that's beyond, that you're not considering. That's the reason why both of them occur. The worst case is case number 3. Case number 3 is that X causes Y. There's a causation there. And because of that, there's an association. The problem is something else is causing y also. And there's that other guy hanging out, z. And z is also causing y. And it's hard to see the connection between x and y because z is always hanging around in the background. It's lurking there behind the scenes. We call it a lurking variable. It's there, even though it wasn't considered. And because of that, it's confounding the issue. It's making it very difficult to see what's going on. And that's really, really bad. So here are 3 different possible scenarios for association between two. In the first case, there's causation, happy. In the second case, there's a common causation. In the third case, there's something else that's causing it as well, which is really messing things up. Okay, so because of this, you can't statistically conclude it's the first case because there's always possibly case 2 or even case 3 that's really going on. The more experience you have, you try to eliminate the possibility of confounding as best you can. Okay? All right. Does that make sense so far? Let's take, if it's okay with you guys, a quick 5-minute break. I just got to get something to drink. Throat's hurting. A lot of talking today. So let's move back at 7:25. Is that okay? All right, 7:25. So you can't statistically conclude any of these situations. That's right. Statistically, you never know which one it really is. That's right.
Hey, Professor. Could I
Yeah.
ask a question real quick? I
I was trying to sign up for Launchpad this past weekend. I tried making a new account. I tried changing my password, but
Yeah.
every time I try to get the textbook or whatever is required with it. First of all, how much is it supposed to be?
I think the two of them together is like 120.
So it's two things together.
It's the textbook together with the online homework. It's all the same. It's
Okay.
one. It's one. One fee for everything.
Okay. Because it says I do not have access to this Launchpad title, and then I click get access.
Yeah.
I enter my password. Okay, it brings me to this page. It says expired, purchase access. And then it just says statistics and practice first edition 1 year access $104.99.
Okay. Well, I think that's the one you want to buy, right?
Yeah, but is it supposed to be a year access?
Well, I mean, you shouldn't need it more than a semester, but I'm pretty sure they give you a year. Most companies like this, they give a year. So.
Okay. But
Yeah, no, it's only for a year.
okay, but whenever you bought it, whoever just spoke, whenever you bought it, did it already give you the online homework, or was it just the textbook? Because for me, it says $104.99 plus tax. Is that what you paid?
Yeah, that's what I paid. I can double check, but no, because I did it before this class. Yeah, no, it gave me the homework too.
But it was
it gave me both.
So the 104 is for the ebook and the homework, and that's for a year.
Oh, okay. So it
There's
already
no other option. That's what you kind of have to pay.
okay, for sure. Thank you.
No problem. Okay. So let's consider the following on slide 37. That's the example that I gave just a few minutes ago. The study of children from 6 to 11 found a high positive correlation between reading ability and shoe size. Do children with larger feet tend to read better? The answer is yes. Children with larger feet do read better, but it's not because they have larger feet. There is a common cause between them, which is age, as we've already spoken about. Okay. Now some of these slides are really kind of screwy, so I want you to skip all the way to slide number 43. And I'm going to show you these on Crunchit as well. They are called residual plots. So first, what is a residual? A residual is the difference between an observed value of the response variable and the predicted value by the regression line. If you look at the next slide, slide number 44, if you look at slide number 44, what we have here is on the left side is the actual data. All those dots are the actual data. There's subject 1, subject 2, over there on the left is subject 11, all these different data plots. And whoever made the spreadsheet either used Crunchit or used some kind of online program, whatever it is. And what they did is they calculated the best fit line. So that red line that goes through the data is the best fit line for this particular scenario. Now, every residual is the difference between the actual Y value. I want to share my screen here so you can see what I'm talking about. Is the difference between the actual Y value and the predicted Y value. So I'm going to change color to blue. No, blue's bad. Let's do purple or whatever this is. So this distance here is the residual for this point. It is the value minus the predicted value. So this up here is the predicted value. And this down here is the actual value. And this particular residual would be negative because the actual value is less than the predicted value. What is this residual approximately? Well, the predicted value is about 2,500. Sorry, the actual value is about 2,500. And the predicted value is about what, 2,900, give or take. So according to this, the residual should be about negative 400. Would you agree? Would you agree? About negative 400? I don't see chats. How do I chats? Okay, so if I go now to the, oh my God, how do I, if I go now, what the, okay, hold on, sorry. This sucks. So if I go now to the residual plot here, and I look at the same X value point, this X value is what, about 430? So if I go to 430, I should find a residual that has a negative 400 value, and there it is. So this guy right here corresponds to this point right here. But instead of plotting the actual data, I am plotting the value of the residual. The value of the residual is how far the actual value is from the line's predictive value. Does that make sense? So the residual plot is plotting all the residuals. And I'm going to go to Crunch It for a second. Let me share again, because Crunch It has this ability. Where do you go, Crunch It? So on Crunch It, what I can do is I go to statistics again, I go to regression, I go to simple linear, and they also have the residuals plot. And when I do the residuals plot and calculate it, you see this is what I get. Okay, I get a line through 0, and it's always through 0 because that's the mean of the residuals, always. And the residuals are either positive or negative, a standard residual plot. Okay, so if I go back to the PowerPoint, which I lost, here it is. So the residual plot is given there to the right of the actual data. Now, if you go back a slide, yeah, go ahead.
So the dotted line between the predicted value and the actual value, that dotted line is reflected in the residual.
Yes,
plot?
yes, exactly. The length of that dotted line is the value of the residual. And that appears in the residual plot as the actual value. So again, on this slide here, let's pick a different one. Let's pick this one right here. Annotate. So let's pick this one right here. So its residual is again negative, and it's going to be about what? Well, this is about 2,600, and this is about 3,000. So this should be about negative 400, correct?
And are we taking estimations just off of what we see, or is it?
Yeah, I mean, if I actually had a, if I actually had the points, I can get an accurate best fit line and do it from there, but I don't. All I have is this picture, so I'm just approximating based upon what I see. Okay. So this is negative 400 at an X value of 580 or so. So if I go to an X value of 580, I should have a value of negative 400. Right? The residual plot gives me the actual values of the residuals, as opposed to me calculating the difference between the point and the line above it or beneath.
But the line is always going to be a mean of 0, so it's always going to be a line straight across 0.
Yes, for the residuals, it's always through 0. That's correct. For the residuals,
the residual plot, it's considered the actual value?
The residual plots tells you what the residual is for each of the X values. So rather than giving me the data, it's giving me the residual. So it plots the residual value, not the data value. Like, look at this data value. It's about 2,600, right? Give or take. Yes? Am I losing you? Have I lost you? Do you have any idea what I'm talking about?
No, yes.
Right?
Yeah.
So the actual value is 2,600, which is nowhere near these values because these values are not actual. These are residuals. It's going to give me negative 400. It's just going to tell me how far am I from the line. I am negative 400 from the line. This distance here is the same as this distance here. I don't care where I fall in the actual scheme. That doesn't make a difference to me. What matters is how far I fall from the line. So if I look at instead this point, I'll use a different color, use bright red. If I look at this point right here, its residual is about, this is about 3,000. So it has about a 1,400 residual, give or take. This distance is 1,400, right? So if I look at the same x value, which is about 670 or so, I should have a value of about 1,400, and I do. The residual plots the actual values, the residuals, as opposed to the actual value, which is 4,500. Yes? Less clear, more confusing, less confusing? Why did I ever take this class? Is it too late to drop? What are we thinking? Okay, good talk. I can't really do much with silence, but more clear. Okay, I didn't see that. Okay. So let's go back to the, we good. Okay, so back to the scatter, to the PowerPoint. So look back at slide 43, right? So we have a scatter plot. On the bottom, it says a scatter plot, sorry, a residual plot is a scatter plot of the regression residuals against the explanatory value, against the x value. Residual plots help us assess how well a regression line fits the data. And you're looking for a random scatter. If you did not see a random scatter, I would be very uninclined to believe that the regression line is appropriate, that it's a linear relationship. One of the things we look for is a random pattern. If the residuals were far away from the zero, and then they got closer like this, that would not be a random pattern. Okay? So we're not doing much with residuals and residual plots. It's more that they exist.
So when you say far away from zero or close to zero, we're assuming zero is the line?
Yeah, like this line here on slide 44, that horizontal line on the right side, that's the zero line.
Oh, okay.
So if all my data on the left was like far away, but all my data on the right was really close, so very, very close, and it got further and further away as we went, I would be very uninclined to think that it was linear and that regression was appropriate. That's a general idea. So now, slide 45. An observation is influential if for a calculation, if removing it would markedly change the result of the calculation. And as an example, look on page 46. If we look on page 46, what we see is the same data. But look at subject 2 on the top right of the data. Okay, if I were to include subject 2, which was there, so why wouldn't you? The data would have an upward trend relationship. Okay? The data would have an upward trend relationship and an R value that was positive. But if I would remove subject 2, that's enough for the linear best fit line to actually point negative. It's still not going to be very strong. R equals negative 0.043. It's still not strong. But it changed it from a positive relationship to a negative relationship. That is enough for me to call it an influential observation or an influential point, because it had the effect of changing it dramatically or drastically, but there is no drastically. That is a made-up word. Okay, but we're changing it drastically and dramatically. Okay, Does that make sense? So if you look at the previous slide, the result of a statistical calculation may have little practical use if it depends strongly on a few influential observations. Points that are outliers in either the X or Y direction are often influential. And they can be influential both for the data and for the regression line. So in that situation, you just want to be very, very careful, because influential observations are a single observation that is markedly changing your conclusions, more so than any other one. What makes that one so special? That's something that might require some analysis. And then we have one last thing we're going to do, which is slide 47. So please turn to slide 47. Okay. So on slide 47, I want you to ignore everything written here and just look at the data. Does that data look positively correlated or negatively correlated?
Negative.
It looks negative, right? Because it's going down. It's going down, right? Now, if you look at slide 48, it's the same data. This time the scale's a little off, which is why it looks further apart than it actually is. It's the same data, but this time with a little more information thrown in. The stuff in the top left, those are all Midwest states. And the stuff in the bottom right are all Northeastern states. Now, when you include that information, all of a sudden it's like, well, forget about negative correlation. We just have two clusters of points. It's not that it's going down. It's that these are all close together, and these are all close together, and they're separated. We have included categorical information in a scatter plot, which in general only works for quantitative data. And sure enough, the X value and the Y values are quantitative. What is the categorical information? That the states under investigation here are in two different locales, the Midwest versus the Northeast. And then you might want to have some analysis. Is okay, why exactly should there be a difference between the Midwest states and the Northeast states? Well, in this case, what are we studying? We're studying the percent of graduates who take the SAT versus their scores. Now, in the Northeast, lots and lots of people take the SAT. 70%, 80%, 90%, lots and lots. And the reason is because that's really what is done over there, okay? The SAT is a standard school entrance, college entrance exam. People take it. But in the Midwest, they don't really take the SAT so much. They take the ACT. Very few people take the SAT in the Midwest. Who takes the SAT? People who are probably applying everywhere, to schools that require the SAT and schools that require the ACT. And therefore, these are your overachievers. These are the ones who might just be better students in general, which is why they have better scores. Had I not included the categorical information here, I would have missed out on that. So how do I include it? Different colors, boxes, circles, X's, dots, whatever you want to do. Just you do something to differentiate them, because everything that you can do that can help shed light on the situation is important from a presentation point of view. And it's not always the math that matters, right? It's the presentation that matters. Can you explain slide 46? Yeah, slide 46 just shows you how it's possible for a single observation to drastically change or affect the conclusions that you would draw from the data. If I did not include subject 2, I would assume it's a negative correlation because my best fit line goes down. And if I do include subject 2, now it's a positive correlation because my best fit line goes up. Subject 2 is extremely influential. With or without, completely changes the data, or at least the results of the data. If you left out one of the ones on the far left, nothing would change that much. Does that make sense? So we call it an influential observation because it really changes the data very much by its presence or by its absence. Anyways, my throat is hurting, and we finished the chapter. I was going to do another chapter today, but I think we're going to stop here because I'm having a hard time talking. So, are there any questions?
Can you explain the last thing you were talking about between differentiating? Like how you spoke about. Well, first of all, I was kind of confused because this graph on 48 shows how people took the SATs. So what were you talking about with the ACTs being included in this graph, or differentiating it, or between the Midwest states? Can you just run over that really quickly?
So, if you just look at the scatter plot, no and no. But anyways, if you just look at the scatter plot, it looks like there's a negative correlation. That as the higher the percent of students who take the exam, the lower their grade is going to be. And on the surface, it seems kind of strange. Why should the grade be lower on average? Because more people take the exam.
Oh, okay.
Okay. But when you throw in the categorical nature that these are the Midwest states versus the Northeast states, then it's not a negative correlation anymore. Then it's like just two clusters, two completely separate, almost graphs, because the data is so different. And then you start asking, well, why should it be this way? And you come up with an explanation, which hopefully makes sense. You can even test that explanation by doing some statistics if you want. But it shows you that when you include categorical information in a scatter plot, it can help shed light on the issue.
Okay.
Yes?
Yeah, get it.
So am I still going to change chapter 2 homework to be doing chapter 2 homework? Are we going that far back? Chapter 2 homework? I thought it was like the new homework or something. Is it chapter 2 that we were talking about? Let's see what's up here. Hold on. Huh?
The one that's due today?
I don't know.
It's due tonight, but it says it's due at 7 p.m. And then the last time you said it was a mistake because I think it's set on Eastern Standard Time.
I thought I fixed
Midnight Eastern Standard Time. No, yeah, but then I looked at all the homework and it still said due at 7 p.m. But I remember you saying that you wanted it to be due at midnight Pacific Standard.
Oh, let's take a look. So, homework 2, assignments, 7 p.m. So you want it to be 11:59 p.m. Is that what you want? 11:59 p.m. Save. How do I save changes? Save changes. Okay, so you have till midnight tonight. Okay, so I just changed it. You have till midnight tonight. All right, you a real G. I don't know what that means, but it's in the beginning of the alphabet, so I'll take it. Then again, if you call me an A, that might have negative connotations. So A, B is bad, C is even worse, D.
Gangsta.
Oh, G's, oh, gangsta? A real gangsta. Thank you. Okay. All right, anywho, I'm going to stop recording now.